Alrighty, welcome to Unit 4, and in this unit we're going to be studying the ideas of probability, randomness, and some random variables. Now, there's a few vocabulary terms that you need to know, and don't worry about memorizing them. They'll come as we are learning the different processes and rules of probability through the situation. But as for now, just here's a brief overview. So, a random process is something that generates results that are determined by chance. An outcome is a result of a trial of a random process. Events are collections of these outcomes. A simulation is a way to model random events such that simulated outcomes closely match real-world outcomes, and thus all possible outcomes are associated with a value to be determined by chance. The law of large numbers here says that simulated or empirical probabilities tend to get closer to the true probability as the number of trials increases. And lastly, we have the sample space, which is a set of all non-overlapping possible outcomes. Again, don't worry too much about the vocab. This is all just hoopla. We're going to talk about what probability actually means in a practical sense. Now, most of us are acclimated here to classic probability, where we take the theoretical amount of outcomes over the sample space. So for example, if you roll a dice, the probability you get an even number, that's 3 out of 6, so 1/2. Or let's say you flip a coin, you toss a coin, the probability of getting a heads is 1/2, right? That's theoretical. Now, empirical is after we run these trials and simulations and studies, what do we observe over what our total sample space included? So for example, I should have different probabilities if I were to toss a coin 10 times versus if I were to toss a coin 200 times. Now, the ways we can model chance behavior depend on what we're trying to model. So for example, you could use a coin if you're looking to model 2 outcomes or 4 outcomes or 2 to any power outcomes, right? So like if we need 8 outcomes, we would toss 3 coins. If we need 16 outcomes, we toss 4 coins, etc. And then each of those sequences would give us the probability of a certain event. Now, or you could roll a dice, and that is great for 3s or 6s because of the way you could do it, like 1s and 4s or 1, 2, etc. Or just regular schmegular old random number generator just to spit out different values. Now, the thing that you do need to take into account, though, is that when we're modeling these chance behaviors, they have to match closely to the outcome. So, for example, flipping a coin, that's theoretically 50-50, so I couldn't model something that's about 60-40 or 70-30. Now, what does probability really mean or actually mean? So let's take a look at the simulation here. I'm going to just move my face here. So again, theoretically, right, we say heads or tails should be about 50-50. So if I flip a coin, let's flip a coin twice. Right now it's heads, so flipping it 2 times theoretically should have been 1 out of 2. Okay, let's flip it a 3rd time. Oh, we keep getting heads. Okay, a 4th time, a 5th time. Okay, now we have 4 heads, 1 tails. Now let me do this 100 times. Okay, we get pretty close here. We see that in 100 trials, I get heads 51% of the time and I get tails 49% of the time. So let me flip it 200 times. Oh, look, here we are, 50-50. Okay, let's do it 300 times. Again, we've had a slight shift here, 400 times, 500 times. And we can see now that in this long run average, they're getting pretty close to being about 50-50. And that really is this idea of probability here. So for example, even tossing a dice, if I were to take the average number of outcomes when I roll the dice, we can see here that in the short run, probability is a little bit spastic. It's just going to keep doing what it's doing. We can analyze some trends, but this is in the short run. So if I do this in the long run, the blue there is the true average. If you were to add up all of the sides of the die, and then divide them by 6, it's about 3.5. So we can see here that in the long run average, rolling a die many, many times, we will closely approach that value. And so probability is essentially the long run average of short run events. So got that. Alrighty, so some basics we need to know about probability. Generally, we call these things probability models. Now there's some notation associated with these. So you can see this P parentheses. Usually there's an X in here because we'll define our X. But P parentheses is interpreted as the probability of. Now there are 2 basics about probability. Probabilities need to be between 0 and 1 inclusive, meaning there's either no chance it's going to happen or there's an absolute guarantee it's going to happen. And to this point in my life, I have no singular events that we're guaranteed or we're not guaranteed to happen. So I'm still struggling with this idea here. But the next thing is that all of the probabilities in that space, in that sample space, must add to 1. So let's take a look at an example here of what this could look like. So the Paul Research Center reported that among mothers, family size is shrinking. And suppose we are to randomly select one mother, aged 40 to 44, and record the number of children she has. And here is the following probability model. So X is our number of children, 1, 2, 3, or 4 or more. And here are the probabilities associated with them. So the first thing asks us to explain why this is a valid probability model. And we have 2 reasons here. And those were just listed. So the first one is that I'm going to look at the probabilities. So 0.54, 0.21, 0.16, 0.09. So my first key point here is that all probabilities are between 0 and 1. And then my second key point here is that the sum of the probabilities in the sample space sums to 1, or is 1. There we go. So if I were to add 54 plus 21, that'll bring me up to 75, plus 16 is 91, plus 9 is 100%. The sum of the probabilities in the sample space here add up to 1, and each of these probabilities is between 0 and 1. So this is a valid probability model. Now let's actually interpret some things here. It says interpret P x equals 3. So in regular English, right, if I were just to explain this to someone who doesn't understand stats, this is saying the probability that the number of children equals 3. What does that mean in context? Well, let's interpret this using our data. So the probability that a mother age 40 to 44 will have exactly 3 children is 0.16 or 16%. So I'll just write those both for you. So yeah, that just tells us that in the long run average, and here, why don't I add that in for you? All right, so in 1 and 6, here we go. In the long run average, equal sign. Yeah, sorry y'all, we just got new computers and I have not learned how to use it yet. But in the long run average, the probability that a mother aged 40 to 44 will have exactly 3 children is 16.16 or 16%. Alrighty, so let's take a look here at some values. The first one says, find the probability that a randomly selected mother has 1 or 3 children. Well, I'm going to write this out. So I want the probability she has exactly 1 or has exactly 3, right? Because I don't care about 2 or 4 or more. I just care about 1 and 3. Well, there at 1 was 0.54, and there at 3 was 0.16. So here, the probability that the mother has 1 or 3 children is going to be about 70%. And again, I just determined this value from our probability model up here. So one moment there. I just added 1 and 3. Okay, now in the second part of the question, or actually part D, find the probability that a randomly selected mother has more than 1 child. All right, so I want the probability that the number of children is more than 1. Well, from this model alone, that would be the probability that X is 2, plus the probability that the number of children is 3, plus the probability that it is 4 or more. Okay, so let's substitute in. So I believe this was 0.21. Here we have 0.16, and here we have 0.9. So the probability that a mother has more than 1 child would be the sum of these probabilities, or about 46%. So there's a 46% chance a mother in this sample is going to have more than 1 child. So that's just some ideas on how to use probability models, and we will practice these in class. There's some live simulations, but let's actually take a look here now at some simulations. Now, when I simulate, I want you to do the following. I need you to imitate this chance behavior. So there are 3 things we need to do. We need to describe how we will simulate one trial. We need to conduct many trials and then use those results to answer the question. So when I say assign, right, one trial, that means if it's 2 outcomes, will you use a coin? If it's 3 or 6, will we use a dice? If it's in 26, will we use the alphabet? Or if it's just 10, why don't we just use the digits 0 through 9? So here, China has 1.2 billion people, and marketers want to know which international brands they have heard of. A large study showed that 62% of all Chinese adults have heard of Coca-Cola. You want to simulate choosing a Chinese adult at random and asking if they have heard of Coca-Cola. One correct way to assign random digits is to simulate. The answer is, all right, so I believe 62% have heard. That is my claim. Now, I want to actually see which of these situations would best model getting a 62% chance of this happening. So here it says one digit simulates yes, the other means no. Well, that puts me into a binary. That's only going to be yes or no. That's not going to give me 62%, so that's out of there. And here we have 0 through 6 is yes, and 7 through 9 is no, but that's going to give me a 70-30 split. And again, I'm after right here, 62%. One digit simulates a result. 0 to 9 tells how many people in the sample said yes. Does not help me. So we need two ideas here, right? Some that are going to say yes and some that are going to say no. So let's look at D and E, and these are going to be very close. So two digits simulate one person's answer, either 0, 0 to 6, 1 or 0, 0 to 6, 2. And those would mean yes. And 6, 2 to 9, 9 means no. 6, 3 to 9, 9 would mean no. Sorry about that. So again, asking which one of these is going to best imitate the chance behavior? Well, 0 to 61, that's 62 digits, whereas 0 to 62 is 63 digits because that 0, 0 counts as a spot there. So since I want to model 62%, this would be my best option here, is that 62% of those would be yes, and the other 38% would be no. So that simulation there is going to best model it. So I would just use a random digit table or a random number generator to keep spitting numbers out to see how many times this happens in a sample of 100. And each of those times I'm seeing how close we're getting to that 62%. I'm trying to simulate the chance behavior here. So again, I would just spit out, here are just two digits. So if that first digit is a 33 and that second digit is like a 74, that's a yes and no. And I'm just going to keep doing this many, many times over. And ideally, if this happens each time, if I'm getting that equal balance, or if I'm showing that a higher proportion of my sample is leaning towards the yes, then we've done this correctly. All right, so here's a few examples to check out some simulations, designing them and whatnot. On the AP exam, you do not have to get this crafty. It's a very weird concept at first. You, again, just need to carry out the following. Describe how you would simulate one trial. Are you flipping a coin, using a random digit table, random number generator, or some other way? Conduct many trials and then use those to answer the question. So here we have 3 examples. So go ahead and pause the video, try these out on your own. Reference your notes or play back the video if you need. So go ahead and start now. Okay, so hopefully not too complicated. And I just wanted to touch back on this problem here. Notice that I said we were only going to spit out 2 digits, which is true, because if it's 0, 0 through 61, there's a 62% chance of that happening between 0, 0 and 99. Same way that between 62 and 99 models that percent of not happening the no. So you're only going to use 2 digits there. And I would keep doing this over many, many trials. Now here, in describing a simulation, on her drive to work each day, Alana passes an intersection with a traffic light, and we believe it's 1/3 chance of being green. So I'm going to use a fair 6-sided die. I'm going to let a 1 or 2 equal a green light and a 3 through 6 equal a red light. And you can do any combination, but as long as there's 2 that represent green and 4 that represent red, because of the way that a die models chance probability. Next, I'm going to toss this die for 100 trials, and I'm going to look at the trials for how many times the die would give a green light. So on trial 1, let's say I get a 1, that's green. On trial 2, I get a 4, that's red. So etc. So it's not just the green or red, the 50-50, but I'm looking because it happens 33% of the time getting a 1 or a 2, that does model the probability of getting a green light at the intersection. So again, we're just looking for those modeling situations. And here, in situation A, we were good to go. We wanted to model 75%, and 3 out of 4 cycles would definitely accomplish this. Whereas in situation B, flipping a coin models a 50% chance, but we're looking for 60% accuracy. So again, we're just looking for the flaws in the design or looking for the correct design. So again, a valid probability model has the following. Your probabilities are between 0 and 1, and the sample space probabilities must add to 1. Simulations are the imitation of chance behavior based on a model that accurately reflects the situation. And we'll describe which method we're choosing. We're going to conduct many trials, and then we'll use the results to answer the question. We're actually going to run a few simulations in class to model this behavior. So that will be the conclusion of our first lesson here for Unit 4, Probability and Simulations.